For the last couple of videos, we were discussing derivatives. We learned what is a derivative. We know that this is a limit of a difference quotient with delta x approaching 0. We also learned different rules, how to calculate those derivatives. Now, what we are going to do is that we are going to learn how to use those derivatives to find relative maximum or minimum of a function. And look, in this context, we're going to resort to the specific interpretation of derivative that we've dealt with a couple of videos ago. And this specific interpretation of the derivative is that derivative is a slope, is that maybe the slope of a function at a given point. And look, we were discussing this in very detail in our video on graphical interpretation on derivative. We said there that derivative can be interpreted as a slope of a function, as a slope of a line tangent to a function at a given point. We will go back to it in a second when I will show you how we can actually use derivatives to find maximum or minimum of a function. But before we go to it, let's discuss what actually those minima and maxima are. Okay, so imagine that this is some function y equals f of x. And look, over here, we simply defined that domain of a function starts from some x0 and ends at some x3. Okay, and look, in this case, we can find 4 very interesting points. Okay, let's start with the point x0. Look, if I calculate the value of the function at the point x0, it's going to be f of x0. And look, what can we say about this value? Look, this value is the lowest value in the entire domain. So, what does it mean for us is that this is a point that we can call absolute minimum. We call it absolute minimum because in the entire domain of this function, from x0 to x3, we will not be able to find a point that simply lies lower. And look, by the same token, we can see that point the point x3 is giving us value of the function f of x3. What can we say now about this point? Look, this point lies higher than any other point in the domain. So how we are going to call it? We're going to call it absolute maximum. Okay, but besides those 2 points, there are 2 other very interesting points over here. And the first one we can see over here. let's call, so now, if x is equal to x1, value of the function is equal to f of x1. What is so specific about this point? Look, this point is definitely not the highest point in this domain. But in neighborhood of this point, it's definitely the highest. Look, we see that the function over here is getting higher and higher and higher. It reaches this point, and then it gets lower and lower and lower. So look, in this neighborhood over here, we can say that this point is a maximum. But look, because it's the highest point only in this neighborhood, we're gonna call it relative maximum. The other term for relative maximum is also local maximum. Both names are accepted. And again, now you probably can guess that the last point of interest is this point. When x is equal to x2, we see that the value of the function is equal to f of x2. And what is so specific about this point? Well, this point is definitely not the lowest, but it is definitely the lowest point in this neighborhood. So we're going to call this point relative or local minimum. And look, derivatives are extremely well equipped to find points like this. So relative maximum and relative minimum. But then you might say, but then maybe they are not that useful, right? Because if those are only relative or local maximum or minimum points, then of course, if I want to find maximum value of some function, it's better to find absolute maximum or absolute minimum. And look, of course this is true, but look, if we find local maximum and local minimum, then what we can do? We can take the two values at the end of the domain, substitute them into the function, and see whether they are actually lying lower or higher than relative maximum or relative minimum, and we will be able to find the absolute maximum and absolute minimum. So those absolute minimum and absolute maximum points can also be those. Look, if for example our domain would be ranging from x4 to x5, you see that in this domain, in this smaller domain, those 2 points represent both, these points represent relative and absolute maximum, and over here it represents relative and absolute minimum. But of course, our focus mainly is going to be on finding relative maximum and relative minimum, because this is why we have derivatives for. Well, this is one of their applications. And if it's needed, we can always look at the endpoints of the domain to see whether we got actually relative or absolute maximum. Okay, now, but we need to remember one more thing. Look, let's look at this graph. It represents a very, very similar situation. Or maybe I didn't. Just to make sure that we have everything the same. Look, what do we see over here? Exactly the same case. Look, if I call this point x1, then over here f of x1 is again absolute minimum. Now, the end point over there let's call it x3 is x4 of course. This point is of course, here we will have f of x4 is absolute maximum. Now, what about those 2 points? Well, this point over here is relative maximum. This point over here is relative minimum. Now, so why are those two situations different? Look, as I told you a couple of videos ago, there are two conditions that we need to have fulfilled to be able to calculate derivatives. What are those conditions? Well, first, the function needs to be continuous, right? So I need to be able to draw the graph of a function without picking up the pencil, right? Now, is this condition met over here? Well, yeah, look, I can quite easily draw this entire graph without picking up chalk. But there was one additional restraint on that. The thing that is prohibited as well in calculating derivatives are the sharp edges. Look here, you see that I didn't draw it like that and like that. Here you see those sharp edges. So the thing is, we wouldn't be able to calculate derivatives at these points. So we are excluding from our interest also the functions that have the sharp edges. So as long as the function is continuous and doesn't have any sharp edges, which is the case with most of the functions we are dealing with, there is no problem in using differential calculus in order to find relative maximum or relative minimum. Okay, so now, knowing what is relative maximum and relative minimum, how can we use our knowledge about the derivative to find them? Okay, look, I will be probably saying and repeating this over and over, is that derivative is the slope of a function at a given point. So look, if I have some function, I calculate the derivative by putting different values of x into the derivative, I'm getting a specific value of the slope of this function at the point for which I'm calculating the derivative. Now, how can we use this knowledge to find? Let's start with maximum. Relative maximum will look like that. You can think of it as a hill, but a very, very slick hill, in a sense that it has no sharp edges. Or what I would prefer for you even to think of it as a cave. Very, very nice cave. Why? I will explain a little bit later. Okay, now, how does the minimum look like? Relative minimum will look like this. You can think about minimum as a valley, right? Between some two hills. Now, it also needs to be very, very slippery in the sense that it doesn't have sharp edges. Okay, now, knowing that this is the shape of the relative maximum and relative minimum, how can I use derivatives to find the points where the maximum actually takes place? Okay, look, derivative, of course, is interpreted as the slope of this line tangent to a function at this point. And look, what do we see over here? If I calculate derivative for this specific point, I see that the slope of the function is positive, which means that the function is actually increasing at this point. Now, if I calculate derivative over here, what do I notice? Look, still the function is increasing, but it got a little bit flatter. If I calculate it now over here, again, I'm getting a line that is upward sloping, but it's even flatter than the latter two. Now, what if I'm going to calculate derivative, let's just say over here? Well, now I see that the slope, the line is no longer increasing. It's actually decreasing. And so what does it mean for us? Well, this means that now the slope of the function is negative. So the function is decreasing. And look, the further and further away I would be going from the top of this hill, the more steep the line would get, right? So, look, if here, basically, as I'm getting closer and closer and closer to this point, this line has a positive slope, but it's getting flatter and flatter and flatter. And going in that direction, over here, this line has negative slope, but it's going flatter and flatter and flatter. So, what should be the slope of this line at the very top? Well, the slope of this line would be 0. Look, this means that at this top of the hill, the line that is tangent to our hill will have 0 slope, and it makes perfect sense because look, if you tilt it even a little bit into the right, you see that actually now we are falling. If you tilt it into the left, we are also falling. And look, how does maximum work? It's a point where when we go closer and closer to it, from the left, we are getting higher and higher, we are reaching this point, and we are getting then lower and lower and lower. So look, in this case, this is the highest point, so it must be between those two cases. And look, this is telling us that value of the derivative at the top of the hill, at the maximum, let's call it, must be equal to 0. Okay, now let's see if we will get similar results with minimum. And look, what is happening if I'm going to be drawing the lines tangent to the local, to this valley? Look, over here we see that it's very, very steep and negatively sloped. Over here, it's still negatively sloped, but it's a little bit flatter. And look, it gets flatter and flatter and flatter as I'm approaching the minimum. And look, if I would do the same thing just from the other side, again, the same pattern would emerge. Here, the function is definitely increasing, right? And rather fast because the tangent line is very steep. Look, as I'm getting closer and closer to minimum, this line is positively sloped, but it's getting flatter and flatter and flatter. So what will I have at the point that is in the very bottom? Again, the slope of the tangent line is 0. So we get the derivative at point x minimum this time. And look, by x maximum, I don't mean the highest value of x. I mean the value of x for which value of the function is the highest. And the same here, this is the value of x for which value of the function is the lowest. Is also 0. Okay, so look, this actually points us into a really good direction. Because it tells us that if I calculate derivative of any function and I find where this derivative is equal to 0, I will find a point that is going to be either maximum or minimum. And this is a very good thing. But I will not be able to tell which one of those it is. Well, but maybe by looking at those graphs, we can actually get an indication of how can we devise a test that would allow us to distinguish between those two cases. And look, actually, we can. Because look, if I'm going to divide this area over here into two parts, I will notice one very specific thing. Look, over here, function is upward sloping. So what I can say about the value of the derivative over here? Well, if the slope of the function is upward sloping, it means it increases, then the slope of the derivative the slope of the function measured by the derivative should be positive. Now, what is happening over here? Well, now we see the function is downward sloping, so the value of the derivative should be negative. Okay, how about here? Here we see that first value of the slope of the function is negative, which means that the derivative is going to be negative, but then over here it starts to go up, which means that here the derivative must be positive. And look, now, knowing those two things, we can actually devise a test. Because look, if this point should be maximum, it is at top of the hill. When we go to the top of the hill from the left side, we see that we are getting higher, 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 higher. Then we reach the top, and then we go lower, 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 lower. Now, if on the other hand side we are in the valley, to reach the bottom of the valley, we need to get lower, 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 and then from this point higher, 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 higher. Makes perfect sense. So, if it happens the derivative on the left-hand side is negative and on the right-hand side is positive, while in the middle it's equal to 0, this must be a local maximum. On the other hand, if the derivative on the left-hand side is negative, it's equal to 0 in the middle, and then it is positive, on the right, it must be a minimum. And of course, look, this is sufficient information for us to get minimum or maximum. But there are some special cases, and there are circumstances in which value of the derivative of the function can be equal to 0 without actually this point being a maximum or a minimum. Let me again illustrate this on the graph. In the next video, we're going to cover specific examples that will make everything easier in terms of calculation, and we'll explain in more detail what we need to do. But let me now just show you a case of the function that looks like this. Like the example is, for example, x cubed, x to the power of 3. Now, let's just see what happens as I approach this point. Look, at the beginning, the function is very, very, very steep. But then it gets flatter and flatter and flatter and flatter. And look, if I'm going to move away from this point, then the tangent line is going to be still positive, but now it's getting higher and higher and higher and higher. So, what should be the slope at this point? Actually, it turns out that over here, value of the derivative is also equal to 0. But look, what is the difference? Look, here, value of the derivative is positive, but it's getting smaller and smaller and smaller and closer and closer and closer to 0. And then, over there, it's still positive, but now it's not only positive, it's also increasing because it's getting higher and higher and higher and higher. In case of this point, you see, we again will have to use the information of what is happening around the point where derivative is equal to 0. Look, if we want to be sure that some point is a maximum or a minimum, then for maximum, derivative needs to change the sign from positive to negative. In case of minimum, from negative to positive. But look, if derivative is remaining the same sign on both sides of 0, this point is not a maximum, it's not a minimum. This type of point we're going to call inflection point. Look, by definition, inflection point is a point at which the function changes its curvature from concave to convex or from convex to concave. But we're going to go back to this a little bit later when we will have more detailed information about this function. Let me just show you that, of course, the same can happen in opposite direction, right? If we would have a function like negative x to the power of 3, this function would look like that. And look, what would be happening over here? Look, over here we see that the function is downward sloping. First, very fast, but it's getting less and less and less steep, right? Then, beyond this point, the function is still downward sloping, but it's becoming more and more and more steep, right? So again, at this point, we would have a derivative equal to 0, but here derivative would be negative, although getting closer and closer to 0. And over here, it would be also negative, but getting becoming more and more negative. Okay, so look, we clearly see that distinguishing whether we have maximum, minimum, or inflection point, because of course this is an inflection point as well, depends not only on finding where derivative is equal to 0, but on the behavior of the derivative around this point in all 4 cases that we have distinguished over here. And look, actually knowing about first derivative is sufficient to establish that. But there is an easier way to do it using the second derivative. And look, this is what we're going to do in our next video. We're going to concentrate on the examples of specific functions, but if we understand how it works in cases of the specific simple functions, we will be able to generalize it to any function we want. And we're going to devise a test that is going to use both first and second derivative, and this test will definitely tell us in which of these cases are we. Whether this is a maximum, a minimum, or maybe an inflection point. Okay, see you in the next video.